Up to this point, we've been computing definite integrals by using the fundamental theorem of calculus. So we have the integral from a to b of some function is the difference between two values of an antiderivative. But this fundamental theorem of calculus requires us to be able to find an antiderivative of our function. But as we've seen, that's not always an easy task, or even possible in some cases. Therefore, we're going to discuss one way to approximate the value of a definite integral. We're going to see a few other techniques in section 6.3, but this first technique is probably the easiest one to think about. We're going to look at what we call the midpoint rule. The idea here is that we're going to take our function, so say the f of x that we had there, we have our limits from a to b, and we want to find the area under this curve, but we don't know how to find an antiderivative. So we're going to take our interval down here from a to b, and we're going to divide it up into pieces. And from those pieces, we're going to essentially cut our region into strips. The area under the curve is just the area under each of these strips, added together. But we could, on these strips, we can approximate them, as long as we make them small enough, by a rectangle. They're all pretty close to being a rectangle, as long as we make them small enough. We could pick a point on our function. So say in this region here, we take that point there on our function for our y value, and find a rectangle with this base and with that height. On here, we could take maybe this point here and approximate it by that rectangle. This one's going to be a little bit trickier to draw because it's actually pretty flat there. Maybe here we actually take that one. I went a little too low. I guess I didn't pick that point. And maybe we pick that point. Something like that. We estimate all those strips by taking various rectangles. There's a lot of different ways we could do this. And in fact, technically, the definition of the integral, if you want to get really picky about definitions, the definite integral really does involve looking at adding up a bunch of rectangles in every single way. But we're not going to worry too much about that here. We're going to make a choice here. We're going to recognize that there are many different choices we could make. We could change the number of rectangles we use. We could look at varying the widths of those rectangles. And which point we pick on our curve is also important as well. But to make it easier on ourselves, we're going to say we're going to use equal width rectangles. That's our first idea. And the second idea is that we're going to always pick the point right in the middle of our intervals. So instead of picking the point on the right-hand side here, I would have picked a point more in the middle. Same on all of them. So we pick points in... Well, I should, instead of just pick points, let's pick the midpoints. That's why we call it the midpoint rule. Now, of course, we're not really going to choose the number of rectangles here. We're going to leave that up to whoever is actually going to be using the rule. If you use more rectangles, of course, things are going to be more accurate, because your rectangles will actually approximate the curve a lot better. But of course, you're going to have more rectangles. It's going to be more work. So let's go ahead and write down our midpoint rule. Or at least the process for the midpoint rule. Again, this is for approximating the integral of f of x from a to b. We're going to choose n as our number of rectangles. And divide our interval from a to b into n rectangles, or in intervals, we should say, of width. Well, if we're dividing a to b, the length of the interval is a minus b, and we're dividing it into n pieces. But we're going to call that number delta x. And we're going to say that delta x is the width of our rectangles. 2, find the midpoints of what we call them the subintervals. All the divisions that we did up here, we go ahead and pick the midpoint of each of those. We could actually go ahead and write down formulas for those. We'll call them x1 through xn. There's going to be n of them. x1 is actually going to be a plus half of delta x. Remember, because the width of our rectangle is delta x. So, and we start at a, so we go half of that distance to get to the midpoint. The next midpoint, we end up, what did I put b? It's still a, but now we add 3/2 of delta x because we've gone 1 delta x to get to the second rectangle, and we went half another delta x to get to the midpoint, and so on and so forth. We could actually write those down if we want to. In practice, we just kind of look at what are the endpoints of our various intervals and figure it out from there. And 3, we evaluate f at each of these midpoints and add them together. So this integral is now approximately equal to delta x times the sum of f at each of our midpoints. Note that what we've really done here is take the area of the rectangles. Delta x times f of x1 is the area of that first rectangle. Because it has a height of f of x1, it has a width of delta x. Same thing with delta x times f of x2. It's just the area of the next rectangle, and so on and so forth. We've added all those rectangles together. This formula just takes advantage of the fact that all of them have a delta x in them. So we can factor that delta x to make the sum easier. So the main part of this is actually just adding together values of the function. Now remember, this delta x we computed back here. This is the b minus a over n. The book actually wrote that in here, but if we've already computed the value, we might as well just use the delta x that we had computed from before. Let's go ahead and do some examples. In fact, we'll just work through a few examples here. We're not going to go too crazy on this. This is can be kind of a tedious process, but so I don't want to bore you, but but it is kind of important that we know how to do this stuff. We're going to start with problem 2, where we have f of x is 1 over x, and we're going to find the area under that curve from 1 to 5, or at least approximate it. In this particular case, note that we can actually find the exact value. We know how to integrate 1 over x. The integral of 1 over x is the natural logarithm of x. If we go ahead and plug in 1 and 5, we have natural logarithm of 5 minus natural logarithm of 1, but the natural logarithm of 1 is 0. So this integral they're actually asking us to approximate is actually the natural logarithm of 5. We're going to find an approximation for the natural logarithm of 5 without even using a calculator. We don't have to. We're going to approximate it using 4 rectangles. So first of all, we're taking 1 to 5, and we divide it into four pieces. So in this case, our delta x is going to be 5 minus 1 over 4. Well, that's just 4 over 4, 1. We divide the interval 1, 5 into into four intervals. We end up with the endpoints of 1, 2, 3, 4, and 5. Maybe we'll go ahead and even let's make this into a number line. If we were to actually draw a picture of this, maybe we'd go ahead and actually draw rectangles or something like that. But I'm gonna make a number line like that. These are our subintervals, and basically each of these intervals represents a rectangle. We're going to take our midpoints, so the points right in the middle of all these. Those midpoints are 3 halves, 5 halves, 7 halves, and 9 halves. You could write those as 1.5 or 1.5 or something like that, but it'll actually be easier to leave them as fractions in this case. That means our approximation, our integral is just ln of 5. So we're approximating ln of 5 by taking delta x. Delta x was 1 times the sum of the function at each of these points. So what is f at 3 halves? Well, remember f is 1 over x. So 3 halves plugged into here is actually 2/3, because all it does is reciprocate our fractions. That's why I wanted to leave them as fractions in the first place. Then we plug in 5 halves. We reciprocate that to 2/5. 7 halves reciprocates to 2/7. And then finally 9 halves reciprocates to 2/9. And we could actually go ahead and combine these fractions. I'm not going to go through all the steps of doing that, but if you do combine them, you get 496 over 315. So kind of a big number there. But the important thing is that if you go ahead and do this division, this is approximately 1.5746. So that is going to be our approximation for the natural logarithm of 5. If we go ahead and use a calculator and actually find the natural logarithm of 5, we're going to see that it is 1.6094 and so on. So maybe not the best approximation. We're close. We got within, let's say, 0.03, 3/100ths of the correct answer. But again, we only did 4 rectangles. We could use more rectangles, and it would take more adding of fractions, but we could get an approximation, a better approximation for the natural logarithm of 5. If we move on to problem 10, this time we actually will end up with a function, square root of 9 minus x squared, that we don't know an antiderivative for. In fact, without using any trig functions, we can't integrate this one at all. That doesn't mean we can't get an approximation for the integral, though. So we're going to try to find the integral of this function on the interval from 1 to 3. And they want us to use 5 rectangles. That's specified in the instructions here. Let's say with n equals 5. So first of all, delta x is going to be the difference here, 3 minus 1 over our n of 5. So we have 2 over 5. That's our width of our rectangles is 2/5. We divide the interval. So maybe I'll even make this a little bit bigger so you can actually see it a little bit better. So we have here, we start at 1. And we go to 3. But we're going at widths of 2/5. So 1 plus 2/5 is going to be a 7/5. Then a 9/5, 11/5, and a 13/5. Of course, if we go to the next one, 15/5 is 3. We need our midpoints in the middle of all these. The midpoint between 1 and 7/5 is actually 6/5. So this was 5/5, so it makes sense. Then we have 8/5. 10/5 is actually just 2. We could go ahead and use that. Then 12/5 and 14/5. So again, I wrote down formulas for these midpoints, but we don't really have to follow those formulas. It's usually pretty clear if we write out our endpoints and our midpoints. That means our approximation here from 1 to 3 of the square root of 9 minus x squared dx is going to be, first of all, we put in our delta x. We put that 2/5 in front. Then we take all of our midpoints and we plug them into our function. What is our function, the square root of 9 minus x squared, when x is 6/5? Well, I'm going to save you some of the work of actually finding that out. Technically here you could use a calculator to find those. I mean, we can't use a calculator to find this unless we have a calculator that can do integrals. But if we use a calculator and do some simplification, we can find that this turns into the square root of 189 over 5. That is f at 6/5. F at 8/5 is actually the square root of 161 over 5. 2 is a lot easier. We can do that one by hand, actually. We have 9 minus 4, so we end up with a square root of 5. The next one, 12 over 5, actually turns out pretty nice. This turns that into just a 9/5, actually. So you would expect the 2 to be the nicest one, but actually 12 over 5 actually simplified nicely. And then finally, when we plug in 14/5, turns into a square root of 29 over 5. Now if we go ahead and plug all that into a calculator and get an approximate answer, this whole thing, remember to multiply by 2/5 at the end, get 4.160145. Let's just say that's our approximation. We could actually go ahead and use GeoGebra to see how close we got to the true answer. So let's go ahead and just put in our function. This is the square root of 9 minus x squared. You might be thinking that looks kind of familiar. Well, the square root of 9 minus x squared is, if you set it equal to y and move stuff around, that it really is just the same as the curve x squared plus y squared equals 9, which is a circle, but it's only the top half. So really, we've been dealing with the circle this whole time. But that doesn't make it any easier to take the antiderivative for. We're going to take the integral of this curve of f from 1 to 3. That is this thing here. And they tell us that that area should be 4.13. Now maybe they rounded, maybe that's 4.125 or something like that. I don't know exactly. GeoGebra just only gives us the 2 decimal places. But it seems kind of reasonable that we got an answer of 4.16. Now notice that if we had actually tried to find it from, say, 0 to 3, we could have used information about the circle that we know. Basically, this is a quarter circle. We know how to, and the circle has radius 3. We could use the formula for a circle, for the area of a circle, and then divide it by 4. But going from 1 to 3 is not one that we really have a standard thing for. Now, we could do some geometry tricks to find it, but really, it's not as simple as it might look. So being able to find this integral using rectangles is pretty handy. Let's try another one. Let's look at problem 20. Here our function, f of x, is 10 over x squared plus 5. Again, this is another function that is not one we can find an antiderivative for. The answer here actually lies in trigonometry as well, but I'm not going to get into anything more than just stating that the integral of this involves trig. We're going to integrate it over 0 to 2 with 4 rectangles. That's what they want in this case. That means our delta x is going to be 2 minus 0 over 4, just a 1/2. Go ahead and make a number line of our points. We're going from 0 to 2. That means we have endpoints of 1/2, 1, and 3/2. The midpoints, well, halfway between 0 and 1/2 is 1/4. Then we have 3/4, 5/4, and 7/4. Those are the numbers that we're going to end up plugging into our function. And so the integral from 0 to 2 of this function is approximately our delta x of 1/2. Then putting in 1/4 in here, again, you could just go ahead and use a calculator right away if you want to. I went ahead and actually worked out what the fraction turns out to be. We actually end up getting a 160 over 81. For 3/4, do all the same kind of stuff. I ended up getting a 160 over 89. Essentially, what's happening here is that when I square the 4 on the bottom, I'm getting a 16, and then I multiply the top and bottom by that 16, and that turns the 10 in the top to a 160. So there's a reason why we're getting 160 on top of all these. But all the bottoms, we have to actually square what we have and then combine it with the 5. When I plugged in 5/4, I got 160 over 105. And then for 7/4, I got 160 over 129. And again, we want an approximation, so we'll go ahead and turn these into decimals, add them together, divide by 2. We get approximately 3.26859. And again, we can go ahead and use GeoGebra to check our work. So our function here was 10 over x squared plus 5. Got a very nice little curve here. We're only interested in the integral from 0 to 2. And it gives us 3.26. In fact, we got pretty close. Our answer, if we were to round it, we'd probably put 3.27. Not sure exactly what the true answer here is. It's only giving us 2 decimal places. But at least we're pretty sure that we did everything right. Now, the midpoint rule can even prove useful in situations where we don't actually have a formula for the functions involved. Let's look at problem 29. I apologize for the low quality of the picture, but this is one where we do need the picture from the book, and I couldn't actually find it in the PDF version that I have. What we have here is a pond, and we want to find the area of the pond. But the only information we have for it is the distance across the pond at 20-foot intervals. What we can do is use the midpoint rule to estimate this area. Of course, in this situation, we're given the delta x is our 20 feet. And the values of our functions are going to be all these measurements. So we're just going to say that the area is approximately our delta x of 20 times the sum of all these things. We have 50 plus 54 plus 82 plus another 82 plus 73 plus 75 plus 80. All of those things. If we add all those together and multiply by 20, we get 9,920. That's actually in square feet because 20 is in feet, and all these are in feet. And that should be an approximation for the area of that pond. I don't know what the exact area is, and we have no way of finding it. But that is as good of an approximation as we have. Now, maybe using some of the other techniques that I mentioned that we'll talk about in 6.3, we could actually get a better approximation. But for what we have right now, this is pretty much as good as we're going to get. So hopefully you got an idea now of how we actually can find integrals that we don't know how to do, that we don't know how to find an antiderivative for, and even situations where, like in this one, there is no function involved. Our function technically we could say is the curve here, but we don't know a formula for it. And actually we'd be finding the area between two curves in this situation. So we'd have to know what the functions are for both the top and the bottom of the pond, and that we're not going to be able to find that. In real world situations, being able to do all this numerical integration, what we call it, is incredibly important. Alright, but I'm going to leave this off here, and I'll see you guys next week for our final chapter. We're not going to do the entire chapter 6, but we are going to do a few sections of it. So I'll see you guys there.